bunch of things. We have an n-dimensional system. We have n eigenvalues. So what are we going to do with the information? Some of them might be positive, some might be negative. What do we do with that information? Well, what we do is we say that to be stable, you have to be stable in all directions. Any perturbation can be broken down into the eigenvectors. If one of them is positive, one of the eigenvalues is positive, the eigenvector, the part of the perturbation corresponding to that eigenvector is going to grow. So to be stable, you have to have all the eigenvalues being negative. And you're going to call a fixed point unstable if even one of them is positive. So that's how you extend the definition of stability from one dimension to multiple dimensions. Okay, in general, in dissipative dynamical systems, which is whenever you have friction, then almost all of the eigenvalues will be negative, and only a few of them will be positive. So you will have reduced your consideration to only a small system. And I think that the next slide, not quite. The one after that, yes, okay, so this one here. So this just says formally what the procedure is. We've been looking at these little tiny polynomials, and you could say, what does that have to do with physics? What does that have to do with mechanical systems? What does that have to do with fluid mechanics? This is a little tiny polynomial. So formally, this is the procedure. The procedure is you have some complicated equations. You can calculate their fixed points and their Jacobians, and then you find the eigenvalues of the Jacobians, and there will be a bifurcation if the real part of one of them changes sign. You can monitor them all as you're changing their Reynolds number, as you're changing the Rayleigh number, as you're changing whatever. You look at them, and when one of them changes sign, then you have a bifurcation. And again, mathematically, nobody really does this, or no, they used to do this. What you can do is you project onto the with the corresponding adjoint eigenvector. That gives you a scalar problem. And then you end up with, if you project it, then you have this many-dimensional system that you projected to one dimension, the dimension in which the bifurcation is taking place. And then you can check out you can do a Taylor expansion about the fixed point, and then you do minimal truncation, and you get, so what everything we just did with these little tiny polynomials has to do with big physical systems is formally this procedure. You have complicated equations, but it's tracked. You can look for the fixed points, and you can look for the Jacobians, you can look for the eigenvalues, and then you would project onto one dimension by taking the scalar product with the corresponding adjoint vector, and then again you would still have some complicated equation, but you could then reduce the polynomial order by taking a Taylor expansion and the minimal Taylor expansion that yields the behavior. And I think there was a question. No? No.
Okay, last one.
Yes, good.
Explain what adjoint eigenvector is.
Yes, I kind of skipped that in the previous slide. Thank you. Okay, we said that there were the V's was the set of eigenvectors, 1, 2, 3, 4, 5. Okay, there's such a thing as, okay, so of course, eigenvector is such that AV equals lambda V. But you can also have something such that VA equals lambda V. And these are the left eigenvectors. Or correspondingly, you can have ATVT equals lambda VT. That's the same thing, just a different. Okay, and those are the, you can see from this calculation, they have the same, I don't know if I did show it, but they have the same eigenvalues. And the left one will allow you to do this projection, as you see here. If you take the Jacobian and you take the product with the left eigenvector, you will end up reducing your size down to the single eigenspace, the eigenvector that corresponds to that eigenvalue. Thank you. So everything that we're doing, that we did up to here, all these things, which were in one dimension, so what is that, is happening in the interesting direction. You have one eigenvalue that's changing sign. Of all those many eigenvalues, they're all staying the same sign. They're all probably negative. And one of them is doing this. And you can project the whole system into an equation that looks like that. And what's that an equation for? What is x? X is the component corresponding to the eigenvalue that is changing sign. And that's the only interesting thing that's happening. Everything else is all just collapsing, is all just negative. You have a dynamical system. Okay, if we were in 2D, then you'd have one interesting direction, which you have all these things happening. And then you have another system in which you just have collapse onto that line. You just have collapse. Now imagine another system. You also have collapse that way. Now imagine a fourth dimension. Ooh, I can't imagine a fourth dimension. But try, and you have collapse onto that one, and a fifth one, and you have collapse onto that one. So all those are not interesting. There's only one that's interesting, and that's this one here. And you're collapsing the governing equations down to that one and seeing the possibilities that happen there. Okay. So that is how these things here are not just models, or just sometimes people think it's a thought experiment or so. It's not a thought experiment. It's an actual projection. It's actual reduction of the true physical system. Navier-Stokes in particular, which is what I know, they really do these things once you've treated them the right way. And we will, the rest of the class will look at examples in which that happens, real big physical examples. Like the cylinder wake, or other Faraday, Rayleigh-Benard, this and that. Okay, now, we had this interesting point about complex eigenvalues. Suppose you had a matrix with, let's say, imaginary eigenvalues for now. Here's A. I mean, the first thing that I said before, this thing here, about doing the Taylor expansion, this part remains true. Okay, and even this part remains true if you define what you mean by this lambda, which is going to be different now. Okay, so this lambda, in the case of purely imaginary, not complex yet, eigenvalues, it will look not like lambda 1, lambda 2, 0, 0, but it will look like this. This is a matrix with an imaginary eigenvalue. I like to think of things in real terms, so I'm not writing I omega, I'm writing this. And what does A squared look like? Well, you can just do this. 0 times 0 plus minus omega times omega gives you minus omega squared. And then, anyway, you can see that the product of this. Okay, and so look, you've seen how well this works. A squared is real and negative, as it ought to be. That is to say, when you take I and you square it, you get something real and negative. Okay, so that's good. It really does look like taking, this kind of looks, maybe doesn't look like I to you yet, but when you see that when you square it, you get something that's negative and real, it starts to look more like I to you. And when you cube it, well, let's take this matrix times this matrix, you'll get something that, oh, it looks kind of like this again. That is to say, it's off diagonal with opposite signs here. So yes, it's true. If you take I cubed, you're going to get something that's imaginary. You're going to get minus I. So that's kind of like what that looks like, right? So you see that these matrices are doing a good job representing I. Yes, okay. And it's not just there, it's not just representation. This is really true. This is what the famous Jordan normal form, it's called normal form, right, for matrices, says that you take a big matrix and you divide it into either diagonal blocks that contain real eigenvalues or blocks that look like this, 2 by 2 blocks that look like this. This is really what that lambda looks like in real terms. So now, here we are. Let's take the exponential, which we're just writing as this Taylor series. So we have the identity, and we have t times this I-like matrix, and this t squared over 2 times the I squared-like matrix, and so on. And now let's recombine them. That is to say, we have here 1 plus 0 plus minus t squared omega squared, yes. And then here we have 0 minus omega t plus omega cubed t cubed, yes. We recombine them, and notice what this looks like. This is the series for cosine, and this is the series for sine, right? So, you know, isn't it wonderful how e to the I theta is sine theta plus I, cosine theta plus I sine theta. I have never gotten over that fact, and here it is. E to the I is giving you cosine minus sine, right? So this is the this is the analog of what we looked at before here. This matrix for the real case became cosine, sine, minus sine, cosine, or maybe the other sine. I always forget which way it is. There. Okay, so that's the exponential of a matrix with imaginary eigenvalues, right? That's what you were getting at. Now, of course, matrices are not eigenvalues are not merely real or imaginary, they're going to be complex. So what do we get then? If you do the same kind of thing that we just did, you would see that the exponential of, a matrix with complex eigenvalues, it will have blocks that looks like this with the minus omega omega, yes. And of course you know that a real matrix has, it doesn't just have any old complex eigenvalues, they occur in complex conjugate pairs. So this is a complex conjugate pair. It's got the same real part and plus or minus I omega. This is representing mu plus or minus I omega as eigenvalues. And taking the exponential of this, if you again combine the Taylor series and so on, you will find that it's an exponential of this diagonal part and then the trigonometric thing with the omegas. Okay. So let us now combine all that. Let's say that we have some real eigenvalues and some complex eigenvalues. Let's say here's a representative one with a complex conjugate pair, lambda 2, lambda 3, and two real ones. And let's exponentiate this matrix, which requires really only knowing how to exponentiate the matrix of eigenvalues. When you exponentiate the whole thing, you're going to have the V and the V inverse on the two sides, and that tells you go into eigenspace, do my exponentiation, and come back from eigenspace. But my exponentiation is done only on matrices that look like this. But now we know how to do this. When we do this, we get a matrix that looks like this. That's to say, the pure real ones just get to be exponentials. The complex ones get to be exponentials times trigonometric functions. Here are our eigenvalues here. And recall the principle that we say that something is stable if and only if one or more eigenvalue has a positive real part. So we can see here as a candidate what's going to happen if we increase the Reynolds number, say, this spectrum is going to move this way, and it's this lambda 1 that's going to become positive here. Just looks as though that's what's going to happen. And then, of course, we would project all the equations onto this, the left eigenvector with corresponding to the lambda 1, we would find out that it was a pitchfork or one of those other things. Okay. So that's what's happening with complex eigenvalues. Okay, and that's perhaps all you had in mind for the moment when you had asked your question, or you have a little more in mind?
Only that.
Only that, okay. So all that's taken care of. And, we have, yes, okay, so before we quite finish with everything, yes, okay, we're still looking at linear bifurcation, so we're linear values. Let's see, we'll stop shortly. I'm trying to think when's a good time to stop. Yeah, let's just finish the linear problem, because we're not quite finished with the linear problem. I acted as though I said that everything could be put in these terms here, right? I said that. I mentioned this Jordan, everybody knows the phrase Jordan normal form for the matrices. It's the one that tells you you can diagonal as a matrix, and you can put it into Jordan normal form. It's what's meant for as diagonalizing a matrix, finding its eigenvalues or eigenvectors. So I said you can always do this, and that's almost always true. And in fact, it is true, and I can tell you why it's true, because you can call computer routines that do this for you. And if you couldn't do this to all matrices, then what would those computer routines do, eh? Well, in fact, you can't always do it. There's a set of measure zero where you cannot do it, and that is called, those are called Jordan blocks. The actual complete Jordan normal form doesn't look quite like that. And let me illustrate this in the following way. Let's look at, okay, we're back to this word node, which we will fully explain. In fact, maybe I could even explain this before. Yes, actually, let me take a little detour. I'm finally in a position of explaining why we say saddle node bifurcation. Why don't we say a stable, unstable bifurcation? Because it's when a stable and unstable point meet. It's because of what we said here. That is to say, we said we're going to say that we're stable when all of the eigenvalues are stable. But we're going to say we're unstable when even one of them is positive. And the usual situation, you're not going to have a one-dimensional system. When do you have a one-dimensional system? Only in little tiny baby math classes. When you are a grown-up mathematician or when you're any kind of physicist or physical scientist, you have many dimensions. And so you don't have an unstable state. You have a state which is unstable in some directions and stable in others. And those points are called saddles, right? Everybody knows about saddles. They, you know, you did F double prime. You know that you have, when you have a maximum or minimum, you check it out by the sign of F double prime, right? If F double prime is positive, you have minimum. If F double prime is negative, then you're like that. But you know that once you get to 2 dimensions, you have several possibilities. It can be like this and like this. You have a bowl, and that's a minimum, or you have an upside down bowl, or you can have a saddle where it does this in one direction and that in the other direction, like a saddle. So what this phrase is telling you is that you don't have unstable points. You have saddles. So when we saw in our little one-dimensional problems a stable point and an unstable point colliding, the stable point was a stable point. It was stable in all directions. But the unstable points were not unstable in all directions. They were stable in some directions and unstable in the others. So they were saddles. So you had a node, which is what is one of those points, colliding with a saddle, and hence the name saddle-node bifurcation. And I think now I'm about caught up with I think. There's nothing quite, okay, on the agenda. There. Okay, so let's get back to this final thing I was going to say. So so star node, and now that's reminding me to use this word node, which is a fixed point, and supposing its Jacobian is a multiple of the identity. So you can see what its eigenvalues are. They're right there on the identity, on the diagonal. That's a matrix with 2 eigenvalues that are both equal to mu. So it's a single eigenvalue, double eigenvalue. Okay, let's look for its eigenvectors. Well, we're going to write mu x1 plus 0 x2 equals mu x1, and 0 x1 plus mu x2 equals mu x2. This is the equation to determine the eigenvectors. Well, everything satisfies that, right? So basically, for this, anything is an eigenvector, and we can choose a basis for the eigenvectors. Well, 1, 0, 0, 1, that makes sense. So anything, any combination of them is an eigenvector. We call this a 2-dimensional eigenspace. It doesn't have just an eigenvector, it's an eigenspace, 2-dimensional. Any vector satisfies this. And you might think this is kind of true, because most likely you have other dimensions, and we're only talking about what happens in these 2 dimensions here. Okay? Now, let us look at another matrix, and you know how many people, everybody knows that if you have an upper or lower triangular matrix, that the eigenvalues are located along the diagonal? Well, if you didn't before, you know now. So, of course, that was the case here, but it's also the case here. So the eigenvalues are, anyway, you could check this also by looking at doing the characteristic equation, mu minus lambda squared, and this doesn't play any role, because when you do the determinant of the characteristic equation, you're going to be multiplying 0 by 1. Everybody agree with me? If you were looking for the eigenvalues of this, when you do mu minus lambda, when you find when the determinant of mu minus lambda 1, 0 was 0, isn't that what you do? I don't see everybody nodding here. Right? Okay. Okay, everybody agree that the eigenvalues are lambda are the solutions to this, right? Okay, so from this this is equal to mu minus lambda squared minus, and then you get 0. So you would still have 2 eigenvalues that are equal to mu, just like before. Okay, and of course that's true, since I just told you that the eigenvalues of an upper triangular matrix are located along the diagonal. Okay, now let's try to look at the eigenvectors. So we're going to write the equations. Mu x1, they're going to be the same as before, except that here you're going to have 1 times x2 because of this 1. So what do you learn from this? You cross this out, and you learn that x2 has to be 0. And what do you learn from this? Well, the same thing that you learned from this, which is to say this is satisfied by all x2. So basically, you learn nothing about x1. So the eigenvectors of this are everything, all multiples of the vector that's in the x1 direction. And that's all. So there's a problem. You're used to thinking that there are as many that you take space and you expand in the eigenvectors. This is a two-dimensional space, but there's only one eigenvector. You can't expand any old vector in terms of one vector here. This one makes sense. This one's fine. But this one not. This is the eigenvalues. There's one eigenvalue of this, which is mu, but there's only one, but it's a double matrix. It's a matrix of 2 by 2, and there's only one eigenvector. You can't expand. There's something missing. And the Jordan normal form took care of that. Here is, okay, an eigenvector satisfies this, and that's what we wrote over there, pretty much. Right? Everybody agrees this is this definition of an eigenvalue, eigenvector. When a matrix is missing an eigenvector, as it just was, you write this equation, and then you write a new equation with that same eigenvalue for some new vector, v, with the right-hand side being an eigenvector. And this new thing is called a generalized eigenvector. So if we solve this here, okay, let's write that down. We write that down the same way we wrote it before. And here this is x, which is anything times x1 here. So we write down our equations. And what we get from this is that v2 is equal to this c here, meaning, which has to be non-zero. Remember that you can't, an eigenvector had better be non-zero, so you can't have a 0 here. So v2 is something like times 1, 0. And that's what you were missing. Before, the eigenvectors that you had, okay, you had 1, 0 here, and now, for the v, you have 0, 1. You have a guy that's in the 2 place. So this x guy, this original x guy, is something which had a 0 in the second place, but the new guy has to have something that's not 0 in the second place. It doesn't actually say anything about the first place, but it just says you have to have something that's non-zero in the second place. So it's the complement of the other ones. So it's non-unique, but that's also true of eigenvectors. After all, eigenvectors could, I wrote this, but everybody knows what you do is you take this to be the basic eigenvector, you normalize, and so you write something that's 1, 0 here. And what do we do for generalized eigenvectors? We not only normalize, but we also declare that it must be perpendicular to the eigenvector. And here's what this looks like in a picture. The eigenvector x has to be, remember, it had to have nothing in this 2 direction. It had to have everything in the 1 direction. But we didn't say how big it had to be, so it could be any of those things. But we just said, oh, let's just normalize to 1. So we picked out this one guy, this red guy, just as a choice. The generalized one can be anything as long as it's not 0 here. The generalized eigenvector is all of these things, but we pick out, for uniqueness, the one that has length 1 and is perpendicular to the x. And I'm going to stop here. So this break of something like 15 minutes.